Hello and welcome to this video about the admittance of a diode when it is functioning as a bridge rectifier diode. This admittance will be expressed as a 5x5 matrix. To summarize what we'll do, we'll firstly draw out this circuit diagram of the bridge rectifier used to transform AC into DC electric voltage. We'll do this by getting data from a simulator of the output voltage using sine functions and exponential decays to get a theoretically exact output waveform, and then using this half-wave rectifier circuit to find the diodes for different cycles of the input. One will find the diode admittance for positive sign input and the other for negative sign input. We'll define some of the voltages and currents that we'll be calculating. Notice that the diode current ID is equal to the load current IC that goes through both the resistor and the capacitor. So we'll firstly calculate the diode model for the two diodes that switch on during the positive cycle using this half-wave rectifier circuit here. Then we'll find the diode model for the two diodes that switch on during the negative cycle that we'll calculate from this half-wave rectifier circuit here. And finally, we'll insert these two models of the diode back into the original circuit and multiply them by a constant that could give us back the same DC output as we got for the simulator. So this is how we'll define the voltage vector that we'll be using to record the voltage across an element. We'll have a DC component A0 and a fundamental harmonic A1 and B1, which is what will be in the voltage source. We'll also have the second harmonic. This is because the ripple isn't in the fundamental harmonic due to the symmetry of this circuit, and thus the ripple voltage will be in the second harmonic and only in the even harmonics. So this is how the voltages and currents will be stored, as these sorts of column vectors, which, when multiplied by these row vectors, will give us the voltage as a single number at any moment in time. So the first step is to get the simulator to get a large matrix of values that correspond to values of voltage in the time domain, represented by columns, and for varying values of load resistance. Each column has a slightly different value of load resistance, which will give us voltage vector values for different ratios of load resistance to load capacitance. We'll use a fast Fourier transform matrix to transform this data into a matrix of voltage column vectors in the frequency domain, also represented here by a 51 by 51 matrix. And then we'll only take the first 5 voltage vectors for one DC value and 2 frequencies of AC, which requires 4 values, so each voltage vector will have 5 values, which will give us a 5x5 matrix. So this is what this matrix looks like. The first column in a green rectangle corresponds to a resistance of 100 ohms and a capacitance of 0.3 farads, which is effectively here 0.3 ohms. The DC voltage, which is the first value, is very large compared to the AC voltage, which corresponds to a bridge rectifier output. The fundamental harmonic is very low, but not zero. This is convenient because zero values here would give us a non-invertible matrix, which we couldn't use in this program. The ripple is contained in the second frequency, which is low, but much larger than the fundamental harmonic, which is expected for a bridge rectifier. It also must be noted that I've only written out these numbers to 4 significant figures, or 4 decimal places, so as to make these numbers easier to read. I've used the big number type in JavaScript, which are numbers which contain 64 significant figures, because the matrix calculations are so sensitive. This is the source voltage matrix, made up of samples of the source voltage for varying values of load resistance. It doesn't vary, and all of its voltage is in the fundamental harmonic. and in the sine function in particular, and 0 in the cosine function. So that's why this matrix has this particular appearance. Then we can calculate the voltage across the diode using these equations at the bottom. So if we plug these matrices into the equation, we'll get this matrix for the voltage across the diode. Now to get the load admittance so as to get the current through the diode, we can calculate this theoretically. This is the admittance for the load resistor, which is this diagonal matrix with equal entries along the diagonal, which is to be expected for a resistor, which is linear. This is the admittance for the load capacitor. It has 0 DC admittance, which means it is an open circuit for DC voltage. It also has these capacitance entries, which imitate complex numbers. So for simplicity, we'll set the frequency equal to 1 radian per second, so that we're left with this simplified admittance matrix. Then finally we'll add them together to get this final load admittance. Now to get the current matrix, we'll multiply each load admittance matrix by each load voltage vector to get each load current vector that we'll insert into the matrix. Each column vector will correspond to a particular value of R and C. This is what the entire matrix looks like. I gave each column its own colour to make it easier to see. And this is what it looks like on one line. It's too long to write out on one line. I've substituted all of the numerical values into it here. And here's this matrix spread over 3 lines. Each column has its own colour. The first column is blue, the second is green, the third is red, and so on. After calculating each column, we get this matrix for IRC, and I've rewritten VD here as well. We know from the circuit that ID and IRC have the same value. And this is the equation that we'll use to find the diode admittance, which is equivalent to current divided by voltage. It must be noted here that I've used big numbers in JavaScript to do this calculation, because it is so sensitive. Big numbers are numbers stored to about 64 digits. I've only written these numbers out to 4 significant figures so as to make them easier to display on the monitor screen. So now we'll substitute these matrices into the equation. So after we perform the calculation, we'll get this matrix, which is the diode impedance for the positive cycle. We'll do a similar computation for the diode in the second or negative cycle. So then we have to get the impedance of the second type of diode in the bridge rectifier circuit that gives us this DC output for the second cycle of the AC input, which we'll find from the same halfway rectifier circuit as for the first diode admittance, only for a negative sign input, and this is it. And this is the matrix of sample load voltages for varying values of R and C. And this is the matrix of sample source voltages, which are all the same and only containing the sine function, with no DC voltage or AC voltages of other frequencies. And so this is the voltage across the diode, and we get this by adding these other 2 matrices together. Then we'll go through the same process of finding diode admittance for these values as we did for the diodes on the positive switching cycle. We'll need to have both of these matrices before we can do the next step. We'll insert these 2 matrices into a SPICE type of program to calculate the load voltage. So then, using a lot of trial and error, we'll find the constant, which can be used to make the diode matrices give the same output DC voltage as the simulation gives for a bridge rectifier circuit, and this is it. And after multiplying these 2 matrices by this constant, we'll obtain these 2 bridge rectifier diode matrix models ready to insert into a circuit simulator program so as to solve for a bridge rectifier circuit. So now to test these matrices, We'll insert the first model in for the diodes labelled D1 and the second model in for the diodes labelled D2. We'll write up this simple circuit file and solve using these matrices for admittances that we've defined earlier. So these are the result vectors. The first is from the circuit program and the second from the simulator, and they look very consistent. I could rewrite it up like this. Here is the ripple formula, just getting the root mean squares of all the different frequencies. The first ripple is for the fundamental frequency, which should be close to 0. It isn't 0 because of the imperfection of the simulator. It contains a bit of asymmetry because it used an odd number of intervals, being 51. The second is that for the second harmonic, which should contain the main ripple that we'd measure. So this is how we'd compare all of the results for varying parameters of this circuit. So here we're varying the load resistance, which will give a varying resistance to capacitance ratio. The results look very good here. So in this case, the phase of the source voltage is varied, and this model is very sensitive to changes in phase, either by a degree or 10 degrees. Varying the source voltage amplitude should give good results, because it is based on matrices, which behave linearly. So I hope that you have enjoyed this video, and especially that you have learnt something new and exciting from it. If you can think of a good name for these diode matrix admittances, please let me know in the comments. Please click like and subscribe if you like this video, and thanks a lot for watching.